Today I'd like to tell you about some work I've been doing with Daniel Romero on egalitarian communities and the networks that underlie them. Specifically, I'll be introducing a new network topology called the nested clique, which has some beneficial properties for egalitarian networks. And I'll be talking about an improved web of trust model that allows us to apply fault tolerance techniques to creating resilient networks. So there's a lot of excitement right now about decentralized technologies. And it's not that the technology itself is the most exciting thing. It's that the technology enables new types of communities. And similarly, the decentralization is exciting because it allows us to create egalitarian communities, or at least it has the potential. So I'll be talking about egalitarian communities from a network science perspective. It's just one way to look at the topic, but it's one that I think can be very fruitful. Let's start by looking at different types of human communities. So we can start with the rugged, self-reliant individual, which is definitely not scalable and not particularly egalitarian. Now, when people start coming together in an egalitarian way, the first thing you probably think about is consensus, town hall meetings, round tables, that type of thing. So it's more egalitarian, but they tend not to scale because as the groups get bigger, communication gets more difficult and things fall apart. On the other end of the spectrum, we have the top-down command and control hierarchy, kind of military style or traditional corporation style. Now, these are more scalable than the town hall meetings, but they're definitely not egalitarian. You have the CEO on top with a lot of power and people at the bottom of the pyramid with very little power. So the big question is, how do we get the best of both worlds? And to shed some light on this, I'll be focusing on the networks that underlie these different types of communities. So for the town hall, where everyone is equal and everyone interacts with everyone, we have the complete network. And for the top-down command and control hierarchy, we have a tree graph with a root and children and children's children. So to create a new network or find a network that combines the best of these, we first have to look at what are the desirable properties of these networks. In order to scale, a network has to be sparse. It can't have too many connections per node. This is because people have a limited capacity for social connections, and if the number of connections grows too quickly as the network gets bigger, eventually the nodes will have too many connections and it won't be able to grow anymore. Similarly, the networks have to have a low diameter. The interactions in a community usually have some cost associated with them, whether it's time or resources. And if you have nodes that are separated by many, many hops, the resources involved in crossing all of those hops can become prohibitive. And as I said before, decentralization can help create more egalitarian networks. In particular, in this talk, I'll be focusing on vertex transitive networks, where every node is structurally indistinguishable from every other node. So no matter what centrality measure you're using, all of the nodes are going to be exactly the same. And finally, we also need high connectivity for a network to be egalitarian. So why is that? So imagine that you have a network and there are a small number of disruptive or failed nodes. We don't want that to translate to a disruption of the entire network if the network is going to be egalitarian. We don't want a small disruption to become big. Another way to phrase this is, if we remove a small number of nodes, we want the network to remain connected. And that's just the concept of connectivity. Well, I'll be using a non-standard measure of connectivity, and to motivate this, imagine trying to disconnect a single node from the rest of the network. If you do it by removing its nearest neighbors, you only need to remove a small number. But if you do it by removing neighbors that are many, many hops away, you need to remove a larger number in order to disconnect that neighborhood from the rest of the network. So as you move further away, a further number of hops h away, it becomes harder to disconnect a network. And we can quantify the connectivity as delta of h, the speed with which that happens. So how does the number of nodes at a given distance h change? So let's look at how these properties come to play in actual networks. A couple of the networks I'll be talking about have been used in parallel and distributed computing for a long time, in part because they have many of these properties. One of them is the m-dimensional cube, and another is the butterfly. And I'll be comparing these to our new network architecture called the nested clique. And to get an idea of what this is, imagine taking a clique, every node connected to every other node, and then replacing the nodes themselves recursively with a smaller iteration of the nested clique, and repeating that until you get to the very bottom. So there's a little more to it than that, but that gives you the idea. So how do these compare in terms of our properties? So this is the sparsity, this is the degree versus the number of vertices. The x-axis is logarithmic. So here we can see that the cube, although it's logarithmic in the number of vertices, it's doing worse than the other ones. So the sparsity is really the downside of the cube architecture. The butterfly is great, it's constant degree, and the nested clique is a little worse than the butterfly. So it's log in the number of vertices. So pretty good, but the butterfly is a little bit better. The diameter of these networks are all relatively similar. They're all logarithmic in the number of vertices, and the cube beats the butterfly by a little bit, and the nested clique beats the cube by a little bit. Now the connectivity is where things really get interesting. So all of these are exponential in h, the number of hops. The butterfly has a constant base to that exponent, but the cube has a base that grows with the number of vertices. Now this is great because we want scalable, high connectivity networks. So if the connectivity increases as the network gets bigger, that's perfect. That's exactly what we want. So how does the nested clique compare? Well, so far for the nested clique, we only have a lower bound. And that lower bound is again exponential in h and has a constant base. So it's comparable to the butterfly, but we have reason to believe that the base of this exponent should depend on the size of the network. So why is that? So the reason is that the connectivity is related to the degree. The reason the butterfly has a constant base is because it has constant degree. And similarly, the cube, the base increases with the size of the network because the degree increases with the size of the network. In the nested clique, the degree also increases with the size of the network. So we're expecting that when we find the actual connectivity, the base should grow as the network gets bigger. Let's apply this to a specific problem. In particular, let's talk about secure communication between distant parties. This has been studied a lot in information security, and one of the most common techniques is the web of trust that's used by, for instance, PGP email. So you start with yourself and your trusted friends, and then you extend your trust to their friends and their friends. This is a great way to very quickly build a large network, but it has a couple problems. One is that it assumes that trust is infinitely transitive, which is not a very realistic assumption. And the other is that it treats all edges as equal. It treats a single trust link as being equivalent to 100 trust links. So it's throwing out of structural network information that we could potentially use. So how do we use this? Well, we replace it with a partial trust model. So we assume that we have perfect trust of nodes up to h hops away in our web of trust. And beyond that, we assume that nodes are more or less trustworthy, but some can and will fail. Now, those h hops buy us a guaranteed connection to several different points that act as intermediaries between us and the rest of the network. We call those the nodes the trust boundary. And because there are several of them that increase with the connectivity of the network, we can use that to implement fault tolerance techniques. We can use the redundancy that offers. So imagine taking the nodes in the trust boundary, picking some number of them, and sending each one a copy of a message. So that's what's on the x-axis in this plot here. The number of messages that we send to nodes in the trust boundary. Now imagine that some number of nodes beyond the trust boundary fail. That's what's on the y-axis here, the number of failed nodes. And I should mention that these are nodes that are these are adversarial failures. So this is a worst possible case. In this case, the color is the probability that all of the messages get blocked or corrupted. Otherwise, you can at least detect an error if it occurs. And the important thing is this big black region in the center. That means that a large increase in the number of faulty nodes can be compensated for with a small increase in the utilized paths. So it's difficult to attack and easy to defend. And even more importantly, this effect becomes more pronounced as delta increases, as the network is more connected. So to recap, I've introduced the nested clique, which overcomes the sparsity limitations of the cube, has similar or slightly better diameter than the cube and the butterfly, and might overcome the connectivity limitations of the butterfly. And I've introduced the partial trust model, which is more realistic than the traditional web of trust and also incorporates network structure, allowing us to apply fault tolerance to creating resilient networks.